So, I'd now like to introduce today's speakers, two members of the UMaine faculty. Lauren Ross is an assistant professor in the Department of Civil and Environmental Engineering at the University of Maine. She's got a fascinating background in applied mathematics and physical oceanography, but boy, is she skilled at working with clammers and aquaculture farmers. Sean Smith is an associate professor in the School of Earth and Climate Sciences and in the Mitchell Center with a joint appointment. And he's an expert in the form and function of rivers and their watersheds. He's worked across a scale of these from the largest estuary in the United States, the Chesapeake Bay, to large watersheds like the Penobscot, the biggest one in Maine, right down to some of the smallest that line the coast of Maine and that drain their waters into Maine's coastal waters, as you'll hear. Lauren and Sean have contributed to really innovative collaborations that involve a lot of faculty and students from different fields, but also a lot of great partners. And they've had a wide range of funding. Some of this work got off the ground with a $6 million grant from the National Science Foundation, and that was called the Safe Beaches and Shellfish Project. They've had other federal funding and funding from private foundations. And I just want to mention that they have just been awarded a $250,000 grant from the U.S. Geological Survey that extends this work to focus on harmful algal blooms that are also threatening the future of wild shellfishing as well as aquaculture. And that was just one of 6 grants awarded in the United States through that program. So congratulations to them. They've got a very intriguing title for today's talk, so I'll let them explain. Take it away.
So as David mentioned, this project, the research initiative, goes back 7 years, and probably before that, before I arrived at University of Maine in 2011, just by collaborations between the Mitchell Center and partners across the state and in coastal areas. Along the way, there's been support. David mentioned the National Science Foundation. That laid a base of research, and then it's continued with different forms of support from the Water Resources Research Institute at University of Maine, funded by the United States Geological Survey. And we are happy about the latest USGS support that's coming up in the next year. But we'd also like to mention that there have been other collaborators along the way that deserve recognition and have been with us for either most or a large part of the research initiative and up through our current activities. And one of them is Bridie McGreevy at the University of Maine, who's been an incredible collaborator for science communication topics, really showing us the way to actually relate to the different stakeholder communities and develop not only a research project, but one that can be used as adaptive management tools and how to communicate that with a large body of people from different disciplines. But also that we're going to talk mostly today about the biophysical interactions or the physical interactions in the coastal areas. But microbiologist Steve Jones at UNH has been highly participatory at different times, showing us different research questions and how he could relate to the biological interactions that are meaningful for the bacteria problems on in the coastal areas. And then finally, Cole Canwood at the Department of Marine Resources. She and her staff have been very helpful to us to frame research questions, to guide locations for sampling and for measuring different types of dynamics on the coast that have been meaningful to our research for many years now. And I would say that we are inseparably linked to the Department of Marine Resources in so many ways. We're really problem solving in a unified way with them.
So one more shout out to acknowledge the hard work of 2 of our PhD students, B. Van Dam and Soheb Ahmed. They've really made great strides in moving this research forward. Okay, so to start out, let's talk about some motivation behind us researching the coastal pollution problem. And let's talk about first the Maine's shell fishery. So Maine's shellfish industry is directly impacted by coastal pollution. And this is a big deal because it's one of Maine's most valuable sectors. Each year, the harvest values reach into the tens of millions of dollars. But there are also social impacts that are not so well known. Mitchell Center research has found that the shellfish industry can impact the economy of local communities, but also their physical and mental health. And these issues can be exacerbated by harvesting closures that are due to coastal pollution. And this makes it important for us to better understand where and for how long harvesting closures should occur.
as David mentioned, the foundation for the project was laid down sometime around 2013 with continuation into 2014 to lay a base of research. And that project, funded by the National Science Foundation, was an EPSCoR project, and colloquially it was titled Safe Beaches and Shellfish Project. But the theme for the National Science Foundation grant was wrapped around the scientific basis for decision making. And you can see in the sustainability solutions world, something like the chart on the right side of this slide shows the complexities of doing this team-oriented, multidisciplinary type of research. But that project could have been a lot of different themes in terms of the subject matter that was involved. In our case, it was coastal processes related to bacteria pollution affecting beaches and shellfish harvesting, with a focus on the rule of thumb for pollution-related closures on the coast. One example would be 2 inches of rainfall in 24 hours being a basis for closures, and whether that needs to be improved, or is that a good enough solution to the problem of managing closures and all the related impacts from those closures. So on the biophysical research front, this comprised a work group that was within the original EPSCoR funded project. So we would meet in a sub-interdisciplinary team that involved biologists, earth scientists, and engineers. There were several problems related to the biophysical portion of the project that we had to deal with. This land-sea connection issue is a really complicated one. If you look at just watersheds draining into coastal areas, they're complicated. They have rainfall coming in from the atmosphere, they have runoff generation processes, and they have the movement of runoff and the constituents carried by runoff down into coastal areas. And then the tidal circulation processes. Everyone knows, if you've ever looked at the coast and waves and currents, how complicated those systems can be. We had the extra task of linking these things together in a coupled system. On top of that, we had the tasks related to science communication and taking this complicated information and putting it into context for public policy, governance, and communities to use for information to help guide their coastal management process.
So the overall goal of our research is to establish new tools for decision making. And we're trying to reach this goal by identifying and quantifying pollution culprits, but also by establishing interdisciplinary partnerships between researchers and working towards knowledge co-generation by obtaining stakeholder feedback as a continual and iterative process. But producing tools that can be easily applied and understood by the user is easier said than done. And why is this so difficult? Well, that's because Earth systems are complicated, and so are people, and we're not alone in this challenge. A recent article that was published in the Washington Post revealed that the National Weather Service has highly accurate thunderstorm forecasts, but the public just doesn't understand those. We really liked this quote from one of the researchers that's working on the project. Sean Ernst said that you can have a perfectly accurate forecast, but a forecast has no value unless a user can make an educated decision based on it. We are trying to manage this in our own research, but the biophysical interactions that we consider for coastal pollution include weather, but also watershed runoff and estuary dynamics, which further complicate the problem.
So the big tasks in front of us, as mentioned, are the explanation of each of these subcomponents of the project. Why do these processes occur in different places with different outcomes, and how they all link together? With the big component of the project from the day one being the interpretation of scientific results so that we can establish whether or not there is a problem or not a problem at different places. So it's place-based research, but scaling up so we can involve predictions across a larger landscape or coastal areas such as the Gulf of Maine coast, and also communicate all this to the community that might use the information to avoid the loading dock where you would just come up with a research paper and provide it to somebody. That wasn't our goal. Our goal has always been to develop those research papers, but also to convey the information in a usable format for decision support tools that the communities can use. You can think of different forms of decision support tools over time that have been used. Down at the bottom of the screen, you see these happy face emojis with different colors on them. Recently, I've seen these in the doctor's office. You can see different pain emojis for smiley face or angry face or sad face. based on the amount of pain you're experiencing. The Homeland Security folks have been using different colors to identify different levels of risk related to national security. The big question is how do you expand that gulf between scientific research outcomes and something as simplified as colors or emojis to actually describe risk? And how do you have the public understand what to do in the face of those different levels of risk in the coastal areas?
So what we found that we need is more comprehensive, specific, and consistent pollution predictions.
So in the early days of the project back in 2013 and 14, we would have consecutive meetings. A lot of times we'd show up at the table with our subdisciplines, and a lot of the team would look and talk about what types of approaches they might take to solve these coastal pollution problems. And this was a point at which you realize that different people have different toolbox and a different approach to solving these coastal pollution problems because they work in either on sources in the landscape, they work on delivery mechanisms, the movement of something in the landscape down into estuaries, or they work in the estuaries themselves. They do sampling, they do modeling, they do different forms of analytical operations. And what our challenge was for just the biophysical science side was to identify what each of those approaches might be and how they would relate to each other. And that was where, at one point in one meeting, this resulted in the development of a ternary diagram to represent the three prominent culprit categories or subdiscipline categories that are going to be involved in the project. Upon a conclusion of that meeting, I remember sending the ternary diagram and the axes to Bridie McGreevy, who reworked it and put a ternary diagram for the social science communication component of the project, which is equally important as all the other parts, if not more important. And she added 3 additional axes on her plot, which were information sources, iterative feedback from stakeholders, and partnership preferences. So each, the biophysical science and the social science, have their own problem space. And then in between them is this co-production space, converting the diagram into a 3-dimensional plot. You can imagine all the complexities and all the parts, but at least at this point, you can actually see where you fit into the larger project and how we can work together. And Bridie informed me that this was, she says, a boundary object. And from that point on, this boundary object has served as a touchstone for the project and the project participants to figure out how things link together. So we're going to focus at this point just on the biophysical problem space in the ternary diagram. If you're an earth scientist or an engineer, you might be familiar with the ternary diagram, looking at 3 different components. Soil scientists, for instance, will use them to take a soil sample and then show in a plot how that relates to the distribution or the composition based on sand, silt, and clay. And if you notice these axes, we have this pollution problem divided it as a function of source, delivery, and residence time culprit categories. And in each axis, the scaling is from 0 to 100, representing the percentage of all causes that are involved in the problem. So on the left side, you see runoff sources, which are the water production on the surface from rainfall. On the right side, you see the runoff delivery. And in the bottom part of the ternary plot, you see the residence times, all from 0 to 100%. If you use this as a metaphor or an example of how you might look at this problem space, look at the dot up in the top of the diagram, and you can see there's a marker in there that has a large size. And for us, that means that there's a bacteria problem that's measurable, detectable, and it's also an issue that's going to have to be dealt with. It's sizable enough to result in potential closure of a beach or a shellfish area in this case. But you can imagine if you're a community manager or at the state level, you would want to try to find some way of addressing that problem. You would want to know if it's a source, delivery, or residence time culprit. So in this plot, you can see that that marker lives in the space at 80% of the culprit problem being associated with the runoff sources, and 10% with the runoff delivery, and 10% with the residence time. And so you can imagine if you knew this, that you would go in there and you'd say, well, I can go in and I can fix these runoff source problems. Maybe it's a leaking septic system. Maybe it's a feedlot on an agricultural land. Maybe it's birds, or maybe it's a seaweed pile on a beach that's generating these bacteria problems. In the case of our original project, a lot of this information came from source tracking information from Steve Jones, who had a lot of experiences in the southern coast of Maine, and finding these different types of sources over time in different places. So if you're a manager, you might say, well, I can go in there and I can put money and people on those solving those problems, but you still have to deal with the delivery issue. So up in the right-hand corner of this plot, you can see excess rainfall, a large thunderstorm event on the Kibo Golf Course in Bar Harbor, where you see runoff being generated and moving as threads of concentrated flow down into Kibo Brook. This delivery problem is an issue to be dealt with because it relates to how efficient is it that you take some problem source of bacteria or some other culprit or pollutant and move it down into the estuaries. So if you're able to collapse that source down and solve it, you might be able to diminish the overall concentration or the source in the water, but you still want to deal with the issue that you're moving it down from the high area to low area and eventually out the door into a place like Frenchman Bay. This might be a case where you're moving it through stormwater devices, pipes. You might think that a stormwater pond might be necessary. You might fix the leak in a pipe. You might change the way that the water can move across a piece of pavement. But this all leaves a measurable, detectable problem still at the bottom end. And you can see in the lower right-hand corner of the ternary diagram, at this point, you have a smaller magnitude of problem, but 80% of the problems related to delivery and still 10% related to residence time and only 10% related to the source.
So in some cases, source and delivery may not be an issue, and the residence time is the pollution culprit. This is essentially a measure of how efficiently pollutants will be evacuated from an estuary. A system that has a long residence time is more likely to have a pollution issue than a system that has a short residence time. Factors that can affect residence time are the freshwater input or the delivery of freshwater from rivers, as Sean was just talking about, but also tidal currents and estuary morphometry, or its shape and size. But more often than not, the pollution problem is a function of all three of the culprit categories. And if that isn't difficult enough, the magnitude of the pollution problem and the variability of the relative contributions of the culprits can vary in both space and time. And this is where we realize that our interdisciplinary collaborative research and research team and our stakeholder partners were living inside of the Schoolhouse Rock song. We have coastal communities that are in the middle of oodles of conjunction junctions, and our team of conductors, which is our research group, are trying to make sense of it all.
So if you went back and listened to the song or looked at the lyrics, the conjunction, junction, and function terms are used in the context of grammar, with the junction being a place in a sentence where you're joining two parts of a sentence. In our case, it's the confluence of coastal watersheds with estuaries. So it made a lot of sense at that point, but also the conjunction is about making connections and quantifying the action of two or more things at the same point in time or space. In a sentence, this is the mechanisms and but nor by which you, or the operators by which you join parts of a sentence. For us, it's the interactions, the conjunction that deals with the interactions between rainfall, runoff, tidal circulation, biological organisms, and communities on the coastal areas.
So now on to the functions. So functions aren't new to us. Most of our scientific life, we use and or derive functions in order to quantify processes. But for this application, functions are about identifying a coastal condition based on drivers of coastal pollution, which we call culprits. And the coastal condition or the pollution problem is a function of the source, delivery, and residence time. The and but portions connect the processes that lead to the coastal condition. For example, we can have large pollution sources and efficient delivery, large pollution sources and long residence time, or large pollution sources but a short residence time.
The or component, in terms of the conjunction family, is related more towards management in our view. You can imagine, as I mentioned in the first biophysical ternary diagram, you might have several different problems in a landscape, but you have a finite budget. So you might choose to actually deal with a source or a delivery problem at any one time, but you would want to know which one has the highest magnitude of influence on the outcomes, not only for a specific type of event, but over the long term. For managers, you also have to solve problems related to deployment of observation information or gear, infrastructure, such as a river gauge or sampling network, or even personnel. So you would want to know if one place is more vulnerable than another, and at what times you would deploy the resources in one place or another. Do you deploy it in large rainfall events, or do you deploy it more heavily in the springtime when the spring runoff is in motion? So these are a lot of decisions, and the or category is highly framed relative to those management decisions that are common along the coast.
So a management response to residence time isn't as easy, because either we would need to change the estuary size or the tidal characteristics in order to lower it, which isn't quite an option for us. So it would be, the management response would be around land use planning or implementing monitoring strategies. For example, you would not want to put a land use activity that discharges polluted water next to a viable shellfish harvesting area. So what we're going to do now is really dig into each axis of the ternary diagram, and we're going to start with source and delivery.
So if you look at the image, it's a map that shows Frenchman Bay. Frenchman Bay is colored in blue, and you see the surrounding land areas. In gray at the bottom, you see Mount Desert Island, the home to Acadia National Park, and it has also Bar Harbor shown on the right-hand side of that island. The stars that are shown are these areas where we've done or are going to do work on river flow monitoring and some watershed modeling. These are study areas or reference watershed sites focused on source and delivery. There are also areas where we monitor flows to set up boundary conditions of freshwater inputs into the estuary systems. So I'm highlighting 3 stars here. Bar Harbor, one of them, it's Cromwell Brook, which is starts at Cadillac Mountain, and I'll show you some examples from that. I'll also provide examples from Crippen's Brook, which is up flows into the Jordan River near Ellsworth. And then most recently, we've instrumented out Kilkenny Stream, which is in Hancock, and it's at the top of the plot there. That is a new addition to our gauging site array. So source and delivery, we're working on measurements and modeling, mentoring, and management applications all at once. David mentioned student participation. This is certainly the case. We've had a lot of people running around in these landscapes to try to add up and map out these different attributes that are meaningful for source and delivery processes related to pollution and runoff processes. So you can see on the left-hand side this map of Bar Harbor and MDI all the way up to Cadillac Mountain. This is the Cromwell Brook watershed. You can see attributes that are associated with this in terms of the coloration and the legend. These are elevations. So the red is for the highest elevations, and it moves down slope all the way to the blue colors, which are the lowest elevations near sea level. Different colors that show up for those elevations, but there are other attributes that are related to the landscape that are important for runoff production. You can imagine that at the top of, if you've ever been to Cadillac Mountain, there are a lot of bedrock areas that are fully exposed, have no soils distributed on the landscape to absorb rainfall runoff. There's also a distribution of different landscape development patterns. In the case of Acadia National Park, it's largely rural with forest cover or underbrush scrub vegetation. But as you work down into the Bar Harbor area, you see impervious surface and an urban landscape, both involved with runoff production in the landscape. And we've mapped these out and confirmed spatial data sets through the landscape that matter to runoff production and the conversion of rainfall into something that can carry pollutants from high areas to low areas in the landscape. You also see the delivery network. It's a system of stream channels and pipes. The stream channels are shown in blue, and you can also see the areas for roads and storm drain networks in Bar Harbor at the bottom end. These are all important to know about because the rate and the timing of movement of runoff down to these coastal areas matters for how we add up these and quantify them in a time series that provide the boundary condition for watershed models. Also, you see the Cadillac Mountain on the top, the Door Mountain to the left, and you see a symbol for the tarn, which is a pond that collects water and stores it in the lowland areas for longer periods of time than other areas of the drainage network. So all this funnels into this concept where we're taking a schematic of developing a schematic of the landscape from high areas to low areas, shown in the cartoon in the center. These have land cover attributes that are shown here at 50-meter grid scale in a sketch. You also see arrows showing the alignments of inputs to the system and movement through the system, with atmospheric precipitation being what's coming in at the top with the black arrows. You see a drainage network shown in blue in the center, and you see the arrows through the drainage network down to a dot on the bottom end, which is the outflow point. you can see all the students that have been involved instrumenting out these places, with a focal point being this outflow, because we're very interested in the hydrologic signature of these systems and how they relate to these attributes, these high areas, these low areas, these distributions of land use and the delivery network. So what do our measurements look like? This one's brand new. This is from last week. You can see the onset of precipitation on the left-hand side of this plot that shows time, October 14th and October 15th. You can also see on the vertical axis the discharge or flow rate, which is in cubic meters per second. This is in Kilkenny Stream on the right-hand side of on the upper side of Frenchman Bay. What this is this is a runoff response shown in blue. So the precipitation event that moved through a few nights ago falls in the landscape, surface water is created on the surface and starts to move down. That rising limb on the left side is where this water is accumulating from more and more places in the watershed down at the gauging location. Eventually, you reach a peak at which most of the parts of the watershed are contributing to the flows that you're measuring at the bottom end. And then one of the most interesting parts to us is this recession limb, which is the gentle leaking out of all these storage bins and puddles and ponds in the upper soil surface area, which is highly variable in different landscapes, especially within urban areas versus forested areas, or areas with a thick soil layer or a shallow soil layer, but in particular, places with a lot of puddles and a lot of ponds. And that's really meaningful to us, and it became a really strong signal that we started to think more about. So we use all this data to actually calibrate a watershed model. And the reason for this is we want to account for different areas, different subcomponents of the water budget. So and here we have evapotranspiration, snowfall, channel flow, snow melt, and we try to put together water balances so that we know the relation between rainfall and runoff. We also want to take a snapshot of time when we have measurements in the field, say it's a month or a year or a single storm. We want to calibrate the model and then run it for longer periods of time, develop a time series. So here's an example. So in the cartoon at the right, you see a map of the Cromwell Brook watershed. You can see those ponds, the Tarn and the Great Meadow, which is near Sur-de-Mont on the right-hand side, shown in those light blue colors. Those are high storage capacity bins that affect the runoff rate at the bottom. You can see in the chart at the left, which is also a hydrograph showing time on the x-axis and discharge on the y-axis. The red line shows that outflow from that watershed measured for a rainfall event. And you see this muted response, a very low peak flow, but a long duration. This is in contrast to the thread of the Kibo Brook that's on the left-hand side of the watershed, labeled as low storage. That corresponds to the blue line and the blue hydrograph on the left side, which shows a very flashy system with a very high peak flow and a very short time interval by which the water accumulates on the surface and moves very fast to steep sloped areas down into the Bar Harbor area. So this is a big deal. These are different hydrologic signatures with the same amount of rainfall, places immediately adjacent to each other. And this is the vehicle by which pollutants move in the landscape. So this can be portrayed in a three-dimensional plot, which if you scale it up using modeling, we can get multiple years. X-axis has the days of the year, Y-axis has the years, and the discharge rates are shown in the vertical axis in cubic meters per second. You can see the spiky nature of the low storage capacity watershed versus the muted response in the rounded curves in the Cromwell Brook high storage capacity area. So this is all related in terms of the physiography and human-built engineered structures such as dams that relate to pond storage, wetlands, and puddles in the landscape. And we found out a lot of this information with a lot of graduate students working on these problems. Brett Gerard in 2018 has a chapter in his dissertation about it. And then Brett B. Van Dam has been working on the distribution of puddles, which can add up to a lot of storage in the landscape in a lot of spaces at one time with a big cumulative impact on the output. Yep. So here we are. We have a collection of watersheds. They all have similar climate, and runoff production is governed by surface geology and soils. We know that. This is pretty much uniform, but those spatial distributions of land use patterns and soils are different in different places. Some watersheds have high storage capacities, other low storage capacities based on the distribution of ponds, but also on the presence of puddles, which are smoothed out with land development activities. And watershed sizes, of course, vary, and they influence coastal conditions differently depending on where you're standing and what watersheds are draining down to your estuary. The question is what is the most important factor influencing runoff delivery patterns? Is it physiography or land cover? So we have to take these water flows and attach concentrations to them for water quality loads. We've been working on this at the same time. The plot at the top just shows a functional relation between discharge on the x-axis and total suspended solids. We know that there's a trend that you can set up from repeated measurements, and we're trying to line that up with bacteria in the case of bacteria pollution. So this allows us to generate our data in a way that actually drives all this water quality load to the door where freshwater meets seawater at the junction. So here we have runoff prediction attributes, the role of surface water storage, attributes important for scaling up to the Gulf of Maine scale, and data and functions for boundary conditions for the estuary modeling that Lauren's team is working on.
Right. So we approach the residence time axis of the ternary diagram in the same manner as source and delivery, with measurements, modeling, mentoring, and considering management applications. The difference is that we're at the other side of our land-sea junction. Here you can see the estuary domain outlined in the white area in the figure. So the measurements that we collect include salinity, current velocity, which are typically driven by tides, and water levels. We use the data collection as an opportunity to give graduate students experience with oceanographic equipment and also data analysis, but also to have experience communicating with stakeholders when the opportunity arises. So we then take the measurements and we use those to calibrate and validate numerical models that simulate the estuary dynamics. And we do this so that we get this information on larger spatial and temporal scales than are allowed by collecting in situ measurements. So the modeling portion of this study makes up a large part of the PhD thesis of my student, Soheb Ahmed. So I have to give him a lot of credit for this. So within this domain, as Sean mentioned before, the stars are the upstream boundaries. They indicate all the land-sea junctions that we include in the model. So this is where the delivery of fresh water comes into our estuary domain. The boundaries at the bottom of this simulation are the ocean, and so those are forced by the tide. So here we're showing the velocity magnitude, and what's important is just to know that the red or the warm colors are where the currents are faster, and the blue colors are where the currents are slower. So once we have confidence in the model simulating the estuary dynamics, we implement particle tracking. And this is to determine residence times. So the figure that you see on the right shows color-coded estuaries where the estuary domains were determined in a meeting with the Maine Department of Marine Resources that was led by Sean's PhD student, B. Van Dam. Once we had these estuary delineations, we inserted particles, which are proxies for pollutants within the estuary. So we're zooming in on one specific estuary just to show the three-dimensional structure of these particles. So you can see the blue particles are at the water surface. We have orange particles that are in the middle of the water column and black particles that are towards the bottom. So these particles are spaced evenly within the domain, and each particle is assigned a tag or a label so we can track where it's going within the estuary domain through space and time. Okay, so the idea is that if fresh water delivers pollutants into the estuary, we can use the particles to determine how long it will take for the pollution to exit the estuary, and this is residence time. So this is a similar diagram that you saw on the slide before. Now we've just inserted particles into the domain. With these simulations, we not only determine residence time, but also connectivity between different estuary systems and the forcing mechanisms that are responsible for driving the residence times. So we know that all of these estuaries have some similar characteristics. For example, they all have a similar tidal range, and they're all at our Land-Sea Junction, which is the place where fresh and salt water mix. The differences between these estuaries are that the watershed size varies, so the amount of fresh water entering into the estuary is going to change, and the morphometry of the estuaries change. The size and shape vary. So the questions that we're trying to answer are, what is the residence time in each one of these systems? And what is the most important factor that influences the residence time? Is it the tides, or is it the delivery of fresh water through river inflow, or is it the estuary shape? So from the particle tracking, we're able to put together residence times maps. So here you can see that the warm colors denote longer residence times and the cooler colors denote shorter residence times. And you can see that these residence times vary significantly from estuary to estuary, but also within the same estuary throughout space. In the background, we're also investigating the flow patterns within each estuary to determine why some systems have an overall shorter residence time than others. So we found that some systems have residence times that are dominated by tides, which is why they are relatively short. In other systems, the residence time is dominated by a combination of factors like tides and estuary shape. And in these systems, we can see that the spatial variability of the residence times increases and it's relatively longer than the ones that are forced by the tide. Finally, we've identified that in larger estuaries that have a more simplistic shape, the residence time is dominated by river discharge. And what we're learning from all of this is how estuary shape and size and tidal range impacts pollution transport. And also, we're finding out in what estuaries residence time is most sensitive to our land-sea junction. So where are the freshwater flows most important? And this is allowing us to generalize our findings, and we're also working to scale these up to the Gulf of Maine scale.
This map that you see here, it shows the down east coast and below in southern Maine as well. This is the process of scaling up that we've been involved with for quite a while, but developing better and better metrics and higher resolution data in different places and different approaches for doing this work. So this is where we take the reference site information, where we've decided or come to some conclusions on what attributes are most important to describing source delivery and residence time culprit categories. And then we're using spatial data as proxies to represent those processes. Once we take those together, we can collect them, and the whole drive is towards getting geographic information organized so that when we have hundreds or thousands of places on the coast, which would be impossible to actually simulate at one time or develop conclusions about, we wanted to see if we could actually divide them out into clusters so that we could manage different settings and relate them to bacteria exceedance events on the in the coastal areas as a method for looking at the relative vulnerability of different places on the coast. And that gets towards the question of where do you deploy resources under what conditions. And so you can see these different colors on the map. Once we take these attributes for source delivery and residence time, cluster them with machine learning methods, we can, in this case, for the example, showing 5 different types of settings, some with high relief, some with high storage, and some with other attributes. And then we take the bacteria samples from the Maine DMR that have been collected over several decades and relate the relation of those bacteria sample outcomes to these different types of clusters, and to see if there's a trend or pattern that shows up. And you can see this in the plot showing clusters on the x-axis on the bottom, and the log 50th percentile of fecal coliform most probable numbers per 100 milliliter on the y-axis, and these different colors showing the distribution of those that ranges of the outcomes from these different sample points associated with the clusters. But this is very difficult for a number of reasons. You can imagine taking reference site data and scaling it up and all the problems that would come around with having to smooth over conditions for land use, for instance, to a size scale of a watershed, forested in urban areas such as in the Cromwell Brook watershed as an example. But then the next question comes up is how do you divide up a space or a watershed contributing to an estuary? This chart off on the right, inset on the right-hand side, is for a place up near, not far from Lubeck on the down east coast. And you can see these different colors showing sub-areas of the watershed draining freshwater flows. So the source and delivery patterns might be different in each of those sub-areas, but we're trying to relate them to one spot, which is that green spot in the upper left corner of the estuary. And it really matters on which sub-areas you choose to relate to that sample point. It also matters where you draw the line on the estuary boundary. And so we're working with all of that now and different machine learning approaches to get at those solutions. So how far have we climbed? We often talk about our project in terms of rungs on a ladder. we started out with a base of research, and we slowly pick off different gaps in our understanding and knowledge and capacity as we move up the ladder. And more questions show up along the way. So far, we've identified attributes most influential to source and delivery from the landscape into the tidal waters. We use that to inform a vulnerability analysis on the Gulf of Maine scale. We also have accomplished this through partnerships and reference site investigations that still go on today. So where we're headed with this, or where does the research stand now? The activities we're involved in at present time in the past year, or a few years up till today, are really associated with our group, the Watershed Process and Estuary Sustainability Research Group, 3 threads: freshwater flow, measurement, and modeling, which is off to the left, and we're still involved with that. Hydrodynamic modeling, which is Lauren's group and SOHEB, and then vulnerability analysis, which B. Van Dam, a PhD student's been working hard on. And these all these threads are being hosted for in terms of the background and the outcomes on a synthesizing website.
So what does the future of our research look like? Well, we're going to continue to try and connect all of the parts, and we're continually finding new parts for our research, and we're working on scaling up and generalizing our findings and scaling up. But through it all, we're going to keep in mind the Schoolhouse Rock jingle to remind us that the main goal of our research is to connect coastal places, people, and science. And lastly, we just want to mention that one of the best parts of our work is the great people that we actually get to work with.
And that's it.
Yeah.
I'll echo, Lauren and I often talk about how lucky we feel to be working with so many dedicated people and so many different threads of science, and also such understanding of the coastal areas, the partners, communities and partners and institutions and the people within them, particularly the students, just to explore this area and put together these pieces of this complicated puzzle has been really awesome and amazing. And I'm thankful to the Mitchell Center for taking such a leadership role in this for so many years.
Thank you. No.
And I think we're going to take questions.
Yeah. Yep.
Okay, can everybody hear me?
Yes.
Terrific. This is Linda Silka, and can everybody give a clap that they can't hear, but that is telling them just how wonderful we thought this was. We all learned so much, and we're not going to remember it all. We'll remember the song, but we won't remember everything that was so great. But if you, the two of you, this was just wonderful. If you had recommendations for who we as the audience should go talk to about what we heard, what would you recommend?
Go.
So one place to go, hopefully within the next week, our website will be going live, and it'll have those threads of research, but also some of the background information on the project. And there are some contact information on the project partners. The Department of Marine Resources is a place that we've always gone to learn more about the activities related to pollution monitoring on the coast and the relation to the shellfishing communities and businesses. We also have other partners in towns that have been very helpful to us, although they're usually focused on much smaller spaces. So if you were in a place in Frenchman Bay, you would find maybe a local community that's associated with operations and shellfishing in those areas. You can see in our presentation some of the organizations that have been helpful to us in different ways along the way.
One of the questions that people had is, what you're doing is so complex and so interesting, and there's a lot that's hard about it. From your perspective, which is harder, the biophysical part or the people part?
Oh, wow. I mean, I feel like connecting them is the hardest part, you know, like coming up with the connections between, you know, the social science and the biophysical science, and learning how to communicate our science in a way that is effective for stakeholders. To me, that That's the biggest challenge. And I mean, of course, the physical science for me is the easy part, but it's boiling it down and putting it or getting it into a product that we can hand over that is easily communicable to the stakeholders and the people that we really want to help. That I think is the most difficult part, but we're trying.
I think that the community part of the project, or I would say the community components of the project, were most difficult for me at the very beginning because I didn't know the people. And over time and through conversations, that changed. And also, I think one of the parts of the 7-year history is that if you stay into a project with tenacity along the way and you see people over a long period of time, those relations get deeper and stronger. I can't tell you how many times we've shown up and you have to learn what to listen for in terms of stakeholder input. We've had funny comments along the way, but all meaningful. One of them at one point was a clamor that asked me the cost of the funding or the funding amount that was associated with the project, and I gave some estimate, and they said, well, you give me that amount, I'll solve this problem. And when you're faced with that, it's difficult to continue the conversation, but it was a great question. And then some other questions on the biophysical dynamics that happen. You also have to listen for. Department of Marine Resources see a lot of things every day, every week, and little snippets of information such as when we see high turbidity, we often see high bacteria counts. And you go to Steve Jones and he says, yeah, a portion of the bacteria can be carried by sediment or particles, and they use that as a vehicle. And so these types of ideas come together, and that's where solutions get generated.
That's great. People who are in the audience are asking, how do you reach the governing entities? And they really vary by scale. What have you found works? And do you ever get frustrated that people aren't quite using all this great work that you're doing?
Well, I would say that Sean's the one that's really established the collaborations with the Department of Marine Resources, so I'll let him talk about it.
I think the interesting part of what you just asked about was, do we ever get frustrated with people not using the information? And I personally, I don't think Lauren does either, get upset about that as much as just the difficulty in finding a way to communicate. And I think we put it on ourselves as a lack of success if we come up with that kind of loading dock situation where we know that we're really satisfied with the modeling outcome, and we put a lot of work into some things that are very difficult to talk about, but we know that they worked. But to parlay that into some that question of, is there a problem, is there not a problem, and what would the emoji look like, is that hurdle is so difficult. And so I think I don't think frustration with the stakeholder or the partner is ever the I'll call it a culprit. It's usually the complexity.
Yeah, I would just add to that also, we want to produce solutions and we want to produce them fast, but it takes a long time for us to gain confidence in our results. And we want to make sure that what we're finding is really sound, scientifically before we translate it over to the stakeholders. And I think I get frustrated with how long, our research takes sometimes because, it is a really complicated processes that we're studying. And so, yeah, that's one additional thing.
Another question is that this great work that you're doing in the areas that you're doing it in are also places where there has been a lot of indigenous work that's been done. So do you have involvement and communication going on with Maine's strong indigenous nations? And do you have anything you might be able to tell us about that?
Not yet,
okay,
but it has been on the radar. And also, I know that colleagues of mine in the School of Earth and Climate Sciences have worked with different indigenous communities. And there's also a geoarchaeology side to this story related to shellfish middens, and Alice Kelly in the School of Earth and Climate Sciences has done a lot of work on that. And those are shellfish deposits. And so this history of shellfishing and what it means to communities on the coast in the long-term, much longer scope than we have been considering so far is relevant. We just haven't gotten to the point where we can
Sure.
segue our research into those questions.
That's great. That's very helpful. Another question that people are asking is, what's your sense of what this experience, this interdisciplinary working with partners, this experience is like for students?
So, I mean, I think that they love it and they get really jazzed about their research whenever they talk with stakeholders and the stakeholders get excited about what they're doing. It really makes them very enthusiastic, to make progress in their work and to clearly communicate their work. So I think it's extremely valuable for the students. And we were actually counting up how many students had worked on this. And I think we came up with like 6 undergraduate students. We had like 5 graduate students. We're also, giving the students in classes experience with, collecting measurements and also like with the opportunity to try and help solve these stakeholder-driven problems. So, yeah.
Yeah, I think again, at the beginning of the project, when we're trying to get our feet on the ground and trying to tackle a Gulf of Maine scale problem, but also do place-based research, it's just an overwhelming wall of tasks and possibilities. And a lot of the responsibility that I personally felt at the beginning was how to simplify that and break it out into compartments so that we knew where we were and so that the student would know, again, in the ternary diagram, where their research fits into the larger picture. I do think that students generally appreciate the fact that there's a potential for a tangible outcome. It's just not going to sit on a shelf in a library afterwards, that there's resources. And I know that grad students that have been in our research group in the past, different organizations and communities and governing organizations have actually appreciated their work quite a bit because they know that they're the ones that day to day are focused on the details. And a lot of them have exhibited fantastic skill and just trying to keep them realizing that they are contributing, and it's a long haul, but they'll make it, is I think one of the big tasks that we have as faculty.
Great, that again is really helpful. Let's suppose for a minute that a group of teachers from high schools all along the coast come to you and say, we'd really like to get our students involved. We'd like them to learn some of what you're doing. They might then stay in Maine, come take interesting jobs, follow you around at the university. What would you recommend for us as teachers if we want to be a part of this very interesting work?
Oh, that's a good question.
So there are a number of stakeholders that we've worked with and also partners, but I'll mention in particular, we did some of our reference site work down at the Wells Estuary Research Reserve, and they have people that actually use their facilities at different times, school teachers and so forth, that go to them for potential classroom activities and opportunities. We haven't adapted our work for high school level consumption, but people talk about citizen science and field activities. I think that there's a general interest in environmental science curriculums and figuring out how the Earth systems work and what our impacts are on those systems. And I think the information that we're finding is we're collecting data and synthesizing in a way, just the colored maps, for instance, to describe that not all places are created the same, provide resources that in the long run teachers will be able to use. That's why one of the reasons we're excited to get this all up on the web. You never know what somebody's going to pick off as a useful component of a curriculum or an activity. And so I think in the long run, we'll feed into a lot of different types of things like that.
You mentioned your great, thank you, your colored maps. Have you ever encountered the challenge of one of your partners being colorblind and a key person that you is really going to make a difference here? And how do we think about that? Or how do we, in other words, how do we make all this work for different groups of people?
That is an excellent question, and I have not encountered it, but it would certainly be important. You can potentially redo that map with different types of designs in those polygons, or you could actually separate out individual maps and show not the full collection of all the spaces for a cluster, but also just individual maps that show where those clusters exist by lines and dark areas. Again, adapting the information. Quite a long time ago, I developed a resource on compilation on explaining how streams work and the way that they look. And a lot of those questions came up because you want to have a broad group that has different levels of capacity, both to comprehend but also to visualize different types of graphics. And I know that there's a lot to that. I think that's a higher level of adaptation that we're not there yet, but that's certainly a place where we'd like to go.
Great.
Oh, by the way, we have taken some of our spatial data, those same maps, and we've cast them up to files that are projectable on Google Earth. And in that case, you could take your mouse and your cursor and push on it and actually have metadata that's shown that comes out and describes what conditions are in that place and what that place might be called. The student that has been working on those maps the most is Bea Van Dam. She's working on a PhD, and she's been very creative in how to develop tools for spatial data analysis. And she has a tool called the Estuary Builder that she's planning on rolling out sometime within the next few months, where you draw a line at the outlet for an estuary, and it collects all the data from the watersheds and the estuary and feeds it down to that pore line, and that provides a summary of information that you can then use to describe a place.
Wow.
So we're excited about that. We're going to apply for a grant to actually hold workshops on how to use it.
Wow. It's just so interesting. It really is. You mentioned Portland as you were talking, or that area. And one question that people have had, so there's a beach in Portland that's the dog poop beach. And if somebody were coming to you, not as a dog poop expert, but as a pollution expert and a kind of the way things move around, and they were coming to you and say, is it a good idea to have one place that this happens? And how would we decide that? Or should it just be spread all over? And what would you say? That's not my area? Or would you say, here's some things to think about?
Yeah, I think that we would you'd have to consider several different characteristics, I would say, that have to do with like the conditions at that beach. Like on the coast of Maine, there's a really extreme tidal range, so you'd have to understand sort of the dynamics of the tide. So when or where different parts of the beach will become submerged with water, so that you can understand if the poop problem will become suspended and be transported to other places where it might cause a coastal pollution issue. I don't think that I would go to them and say, I think that you should do this or that, without really trying to look into the physics of the area to see, what the residence time is and what some of the physical or estuarine or coastal dynamics are at that location.
Do you have final thoughts for us? We're just about out of time, and I know, there are just so many additional questions people have about harmful algae blooms, about the mapping, about the all kinds of different things. Do you have advice for us so we can be of assistance to you?
Oh, that's nice. Well, I'll just say that we are really excited about adding, the harmful algal bloom dynamics to our coastal pollution or water quality research. We're going to use the particle tracking as proxies for pseudo-niche blooms, which are the toxic diatom that produces amnesic shellfish poisoning. And we're going to start that work really soon, and we're super excited about it. And I don't know about advice.
Well, I guess once we get the website up and running, it would be a place where you could go and move into one of those threads that interests you most, whether it's vulnerability, estuary circulation, or freshwater flows, and you could develop some questions and send them to us. I think the more conversations we have, the more we learn, and the more we move the information out to a broader audience. And so I think that would all be healthy. I'm excited about this process. 7 years ago till today, really learned a lot about the different coastal dynamics and places and the communities living within them. And well, we're just looking forward to continuing to assemble the information. The website became necessary for the exact thing that you're asking about, is that there are so many people that inquire about different parts of it, and it's so complicated to talk because they all intersect. One of the problems with all these connections is that it's hard to talk about one part without explaining how it fits into the rest of them. And the website's going to help with that. It was also a matter of so many people participating, and that group, the watershed process group that we've described, is a collection of people, and it's much easier to show them on the website and show this array of this population that's dealing with this issue in an organized way. And so I'm hoping that steers people more directly towards what they want. Wonderful.
Ruth has kindly put your email addresses up in the chat so people can follow up. You're going to be overwhelmed, but it's people who really care. And let's give them a hand. Thank you very much for a terrific, interesting talk.
Thank you.